Let's begin with the next section of elimination reaction, which is the E1 mechanism. As you remember, we just finished the E2 mechanism, which is a bimolecular reaction. In this case, we'll just look at the elimination reaction, which is E1 mechanism. E1 because it's a unimolecular reaction, only the alkyl halide is implicated in the slowest or rate determining step. So here you have a tertiary butyl iodide in the presence of water, which is acting a weak base. Remember, water as a weak base to form this isobutylene eliminated terminal olefin. It is just dye-substituted alkene is formed from this reaction. So this went through E1 mechanism. So the kinetics for, just to remind you again, the rate of the reaction is K rate, that's constant, times the concentration of the iodide, the alkyl halide, in this case a tertiary butyl iodide. Obviously it's a unimolecular, that's why we call it E1, just one the unimolecular nature of the elimination reaction. When it comes to the mechanism, this is a mechanism, the lower portion here you see is, that's how the mechanism is, or that's how you show the arrows. So the first step is, which is the slow step, is the halide or the electronegative atom or the leaving group first leaves. That is the first step. That is the slow step. It's a slow step, and it's a formation of a carbocation. Once the carbocation, which is relatively stable carbocation, you need to have that kind of carbocation, then the next step is the abstraction of hydrogen. So first carbocation formation, carbocation is formed, formation, step 1. In the step 2 is the abstraction of hydrogen by a base, abstraction of hydrogen. That is the acidic proton, relatively, the alpha, the beta, this is beta carbon, this is the alpha carbon. From the alpha carbon you lose the halide to form a carbocation. From the beta carbon, now we are abstracting hydrogen, just what we did in the E2 mechanism. So here a very weak base, such as water, can abstract that proton. So the proton would be abstracted by H2O, and then this bond collapses to make the double bond, to just generate the alkene. So this is the mechanism in terms of E1 mechanism. So initial formation of a carbocation followed by the abstraction of hydrogen to form the alkene or the double bond. In terms of energy diagram, which is a unimolecular reaction, that means it is a two-step reaction. First, the carbocation formation is the highest energy, which is formation of the carbocation through this transition state. That means in the transition state, the carbon-iodine bond elongates and it's about to break away. When it breaks away, you form this carbocation. But this is how the transition state looks like. In the transition state, as obviously predicted, you would only have the alkyl iodide. After you have the carbocation formation, the next thing is a relatively faster process of abstraction of hydrogen by water molecule to form this double bond, and finally you have the isobutylene product. So this is final product, alkene product. These are starting materials. The starting materials are the tertiary iodide and obviously it's water. So that is the starting material, that is the product. So E1, This is the same product, meaning the final product is an alkene, but it is always going through a concerted, it goes through a single two-step. A first step would be a carbocation formation. At this point, I want to highlight some very important point. You need to go back and remember what an SN1 reaction is. An SN1 reaction is when the water molecule attacks the carbocation. So always SN1 and E1 are competitive reactions. It is possible that you would get an SN1 product, which is a substitution product, and you should also get an E1 product. So depending upon the situation or the condition, you can favor one over the other, whether the alkene formation or the substitution product. So SN1 and E1 are competitive. So similarly in E2 case, it is also competitive by SN2, but here this competition is very significant. If you see an SN1 product, which is an alcohol, and at the same time if you see an E1 product, which is an alkene, then you should also say that yes, because in the mechanism there is competition between SN1 and E1. So if competition happens, what you see is, would have seen is a product which looks like this as well. So you should be mindful of this. SN1 and E1 are competitive. So you get an alkene product through E1 mechanism, and at the same time the SN1 can give you also that tertiary butanol compound. So if you see in an exam or quiz, you would find that two products are formed there. So you need to remember they came from an SN1 mechanism and an E1 mechanism. So we'll continue more on. The nature of the alkyl halide also is important in the same what we saw in SN1, SN2, E2. Here the alkyl halide, the nature of the alkyl halide is important, where the E1 mechanism to happen, you always need a highly substituted alkyl halide is important. So metal halides, they don't undergo E1 mechanism because you cannot form a metal radical, a metal carbocation. So CH3 carbocation is very unstable. It doesn't form. So as you see, the E1 mechanism needs carbocation formation. Primary is not also as great to form a carbocation, but the most stable one that would be formed is very stable, relatively very stable carbocation can be formed as you go from primary to tertiary. So the rate of the E1 reaction is higher for stable carbocations because they can easily form because they are very stable. They are easy to form because they are stable. So the rate increases as we go from primary to tertiary. So one, that is very important. So for E1 mechanism, you always need either a secondary or a tertiary alkyl halide. In terms of bases, what you use in E1 mechanism, E2 always needs a very strong base. So E2 always a strong base, while the weaker base can also be applicable in terms of E1 mechanism. So for E1, weaker bases are okay, such as even water can do the reaction. So that's for E1 when it comes to basicity. Regio-selective, that is what it means, is that like we have a Zaitsev rule, where a more substituted alkene is a much more favored or a major product, it still holds true with E1 mechanism as well. So regio-selectivity comes from more stable alkene. Let me do this one more example for E1 mechanism. As you see, you have a tertiary alkyl halide. This is cyclopentyl bromide, a metal cyclopentyl bromide. So this carbon right here is a tertiary, and the leaving group is bromine, which is also a good leaving group. Iodine, bromine are good leaving groups. So in presence of water, first what happens is the slow step, which would form the carbocation, right? So by E1 mechanism, I have CH3, which is here, but after bromine has left, you would have a carbocation formed like that. So in this carbocation, you have, this is the alpha carbon, obviously. And how many beta carbons do you see for this? You have this beta carbon and this beta carbon are the same. They are equivalent. So you have here or here. So this is one beta carbon, two hydrogens there. But remember this one. This is also a beta carbon. That's when the regio-selectivity, or by Zaitsev rule, a more substituted alkene is what you form as a major product. So water comes in, one of the hydrogens from here, water comes and abstracts that proton. This forms a double bond over there. So that would give us this product. This is one product. How about if I took one of the protons from this beta carbon? Always the beta carbons, they tend to lose that proton. So if you abstract one of the hydrogens from the CH3 group, you would form this product as well. So you would form this product, double bond across that bond. So if you just look at here, because the alkene formation is regio-selective by Zaitsev rule, which one is the major product between these two? So the major product in these two would be, the more substitution would be here, this alkene, right here, this double bond is tri-substituted. One alkane group here, one alkane group here, alkyl group. So this is a tri-substituted alkene, tri-substituted. But here, this is hydrogen, these are hydrogens, obviously. So this is a di-substituted, one alkyl and one alkyl here. So this is a di-substituted. So between a tri-substituted and a di-substituted alkene, and this is also an internal double bond, so this would be a major one. So that's a major compound, a major alkene. Let's summarize the E1 mechanism. So far we have seen all the details, what's required in the E1 mechanism of reaction. So these are the summary of E1 mechanism. So this would conclude all about the E1 reaction mechanism. So in terms of kinetics, it's a first order reaction. That means in the transition state, only the alkyl halide is implicated. That means rate is dependent only the concentration of alkyl halide. As far as the mechanism goes, it's a two-step reaction mechanism. That means a carbocation is formed. That means the most important or rate determining step of this reaction is a carbocation formation. It is a two-step. That means first the carbocation would be formed, then the elimination of the beta hydrogen continues in the second step. So the identity of the alkyl halide is important in the rate of reaction for E1 mechanism. E1 favors mostly tertiary alkyl halides because you are forming a stable carbocation that is important in the first step. So carbocations that are formed from a tertiary alkyl halide followed by secondary carbocations are important. Almost nothing happens as E1 with a primary alkyl halide. Of course, metal halides would not do. For example, metal halide does not completely do. Even the primary one doesn't do. So, most favorable for E1 is the tertiary alkyl halide. As far as bases are concerned, weaker bases like alcohol, neutral ones, water, very neutral electron donating or that can abstract hydrogen easily from the carbocation is sufficient. So it requires only weaker bases can do. As far as leaving group, obviously the carbocation forms if you have a good leaving group. So good leaving groups like iodine minus are important. As far as solvent is concerned, still its polar protic solvents are required. So those are like alcohols, water, and so on. So protic solvents like acetic acid or so on are important or necessary. As far as the E1 reaction type, when it applied for any meaningful synthesis, is not very useful. The reason is it's competitive with SN1 mechanism. If you remember back, SN1 mechanism is a mechanism where a substitution happens by a nucleophile. So if as far as the E1 is in the E1 a stable carbocation is formed, an SN1 side reaction can happen. So it is competitive with SN1 mechanism. Hence, it gives you a mixture of substitution product, elimination product, and so on. So it's not very useful as far as meaningful synthesis problems are concerned. So the competition is E1 competes versus SN1. So that competition makes it to produce several different products in the reaction mixture. That means you can have an E1 reaction and an SN1 reaction in the same, from the same substrate. Hence, it's not very useful to use an E1 mechanism in a meaningful way for a synthesis of a natural product. So with this, we'll just conclude about E1. So there are important aspects of E2 mechanism that we will consider in the next video. So this is a conclusion or a summary of an E1 mechanism of our elimination reaction by E1 type. So we'll continue. The discussion on the stereochemistry of E2 reaction is very important because there is a requirement where the alpha proton, the beta proton, and also the alpha halide should be antiperiplanar. What it means is that if you have a stereochemistry such as this, both the hydrogen that's on beta carbon and the halide on the alpha carbon are in this configuration. This is a free rotating compound because it's a sigma bond. You can have several Newman projections for this. So in E2 reaction, the requirement is that the syn periplanar would not produce an elimination reaction because both are in the same phase and on the same plane. So syn periplanar means that both the hydrogen, which is on beta carbon, and alpha should be antiperiplanar, like that. So when we say syn periplanar, they are on the same plane, like this. And if you just look at here, on this plane, both the hydrogen and the leaving group are on the same plane. So when a base comes in and obstructs this, this has to be in the opposite direction. So if you just rotate this into 180 degrees, you would have something like this. That means the hydrogen on the beta carbon and the alpha halide on the alkyl halide would have an anti-configuration. Anti means 180 degrees. So this hydrogen and this halide are at 180 degrees. If you just rotate, keep the front hydrogen B and A, hold it there and rotate this by 180 degrees. D would come here, C would come there, and A would be here. So this is called antiperiplanar, meaning that they are on the same plane. If you just see this as a plane, both hydrogen and X are on the same plane, but in anti-orientation. So this is the beta carbon. So on the other carbon, this is on the alpha carbon. So both are on the same plane, but in 180 degrees one another. So this is important for an E2 reaction. So the E2 reaction is stereo-specific in a way that it requires the hydrogen and the halide should be at 180 degrees, especially in the open conformation we have, that can be easily achieved. So syn periplanar would not produce E2, good for E2, but antiperiplanar arrangement is good for an E2 reaction. So this is the stereochemical relations or the stereochemical requirement for an E2 reaction. So let's see this. This is when you look at here, this is the alpha carbon and this is the beta carbon. So this compound has stereocenters. So if you just look at the stereochemistry of this is an S and an S configuration. Both are SS. So we are using etoxide as a base. This is etoxide. It is a strong base. So it pulls off this hydrogen and this bond comes back here and this leaves. That is the mechanism of an E2 reaction. In this case, the product you would get is very specific because this is antiperiplanar arrangement. Now, because this is important in E2 reaction, first you have to align them so that the hydrogen and the bromine would be antiperiplanar. So when they are antiperiplanar and this elimination happens, both this CH3 and the phenyl group C6H5 would be on the same phase, and this C6H5 and this hydrogen would be in the same phase. So you would produce a specific alkene by the elimination. So CH3, as you see, is into the plane of the board. C6H5 is also in the plane. So it will remain as such once you arrange it in the antiperiplanar arrangement. So this alkene is the major product. And if you start from an RS configuration, when this is R, that means opposite to this one, and S, and you arrange this into periplanar, antiperiplanar, the base comes in. Still you have to arrange it because it's free rotation. You lose that. So now the C6H5 and the C6H5, which is two phenyl groups, would be in the same phase. And the CH3 and the H would be in the same phase. So you produce this isomer. So the products are not the same. These are different isomers of the alkene. Here, if you start from an RR, always arrange them by rotating it into this configuration, this and this are antiperiplanar. So now the elimination reaction would produce C6H5 and hydrogen in the same phase, and the metal group and the C6H5 would be in the same phase, producing this product. How about if you start from an S and R? So we have two stereocenters, 4 different compounds. So now if you just do this elimination with this one, you will produce hydrogen and CH3 on the top, or one phase, and C6H5 and C6H5 in the same phase. So if you just look at here, you are producing from SS and RR. Actually, they give the same molecule. They are the same. If you just flip this up, this and this are the same. So if I just label product 1, 2, 3, product 4, 1 and 3 are the same products. So this from SS configuration and RR, mirror images, they produce the same product. Compound 1 and compound 3 are the same. And RS and SR, the mirror images, also would produce compound 2 and compound 4. These are same molecule. Same. But you have to always be careful by arranging them antiperiplanar for a free rotating alkane. So E2 reaction, to recap, it needs antiperiplanar arrangement between the beta hydrogen and the alpha halide. So that should be an anti-configuration. In all of them, we have arranged it so that they are anti. Here, this and this are anti. This and this are anti. This and this are anti. So you should be able to do the Newman projection or also mentally rotate the anti-configuration. One more new concept here I want to introduce would be the E and Z isomers. What are E and Z? E is for trans, Z is for cis. So E is integgegen, it's a German word, to be opposite. So these are trans, basically what you know. So Z is zusammen, I think. This is together or same. So this is cis. So from SS you produce an E isomer. From RS you could produce a Z, and for this case, for RR you produce E, which is the same. Same with the compounds. Now, so E and Z are cis and trans. It is the same nomenclature. So how did we assign E for this? Always you should compare the ones from the same side and same side, not this to this. You always compare this and this. So if you just look at CH3 and C6H5, the priority goes for the 6 carbon than the 1 carbon. So the priority is down here. But here, if you just compare between these two, the priority goes to for this. So they are opposite. That's why they are E. Again, you don't compare this to this. You compare the ones which are up and down, not side by side. So if I compare this with this, the priority would be for this. And if I compare this with this, the high priority would be here. So the two high priorities are on the top. They are Z or cis. Again, here, between these two, the priority would be for cis6H5, high atomic number, high number of atoms. If you just compare this with this, priority would be for this. So opposite. High priorities are opposite. It's an E configuration. For this one, if you just compare this with this is high priority. If you compare hydrogen with this is high priority. Both large groups are on the same side, therefore they are Z configuration. So always remember the E and Z configuration for an alkene. It is just equivalent to saying cis and trans. The way you'd be comparing would be not from same side on top, but rather from the same bottom and lower and bottom atoms. So compare these two, and then identify the E and Z. With this is an E2 mechanism of reaction when things happen in the same time, bases abstracting hydrogen, and bond is formed, and the halide E2 mechanism requires antiperiplanar arrangement between the leaving group and the hydrogen. Now, these are freely rotating compounds, which is very easy than if you have a locked one. For example, if you have a ring system where it cannot rotate, you only have one possibility. So that's what we're going to look in the next video, how would come up with a product for antiperiplanar elimination. We have seen an open system, like an alkane that's not cyclic, acyclic ones for E2 reaction. We can just arrange the molecule by rotating it so that the alpha halide and also the beta hydrogens would be antiperiplanar. In cyclic system like cyclohexane, for example here, the chlorine, which would be on the alpha carbon, and potential beta hydrogens are this. But as you imagine now, there is no periplanar conformation for this, because if you just look at this and this are not on the same plane, and there is nothing that is the same plane for the hydrogens for this elimination to happen. So what we're going to do would be, we can test the other conformer, meaning the other chair conformation. The other conformation would put the chloride, which is the leaving group, on the axial position. Even though it's not a more stable conformer, the reaction happens from this conformer, not from this one. So if you just look at this carbon-chlorine bond and this carbon-hydrogen bond are on the same plane. At the same time, they are antiperiplanar. So this has antiperiplanar arrangement that's required for an E2 reaction. But here, they are not. If you consider this carbon-chlorine bond, this hydrogen is not on the same plane. This hydrogen are not on the same plane. This hydrogen is not the same plane. So there is no any hydrogen that can be abstracted for the reaction to happen. So the reaction would happen on this one. So we use a base such as ethoxide, CH3, and it would abstract that proton. The bond would form on this, and this leaves. So always when you have a cyclic system, you have to find a conformation that would give the antiperiplanar arrangement to get the product. So the product of this elimination reaction is this double bond, which is equal to an alkene, cyclohexene. So an important examples which I put here, a chloromethyl cyclohexane, when they are cis and trans. Those are two different compounds where you have this is a cis because the metal and the chlorine are in the same phase. So the first way to consider this would be just make the chlorine always, or the leaving group, on axial conformation. So the conformer would be this conformer. Let's see how it looks like. Chloride would be axial, and here the metal group would be equatorial. So in the two position, it would be equatorial. So this would be hydrogen axial, metal group equatorial. So this is what the conformer looks like. Let's do the same thing on this one. Because the chloride is in equatorial position, you will not find any conformer that makes the chloride on the same plane. So let's convert this also into the other conformer. So from this conformer, if I flip this, ring flip, actually this is not, this is less stable. So I have this conformer, this chloride is axial, this metal is also axial. So this is just for problem solving purpose, this is an initial thing you have to consider first. You need to have the halide or the leaving group in this situation in the axial position when you use cyclohexanes. Now, if you use a base now for elimination, E2 reaction, let's use OCH2, CH3. Let's consider how many beta hydrogens we have. So there is two possibilities. This is one of the beta hydrogens that can be eliminated, but there is another one as well. Here is two hydrogens. One of them can be used. This hydrogen and these two hydrogens are available for elimination. So first let's eliminate this hydrogen. Taking that, you would get a product something like this, meaning that this is CH3, but the double bond is right there, 1. But by eliminating this also, you would get another product, which is I believe, yes, two products. This is a 1, 2, 3 position and a 1 position metal group. So which one is major product? By Zaitsev rule, Zaitsev rule gives you a more substituted alkene. More substituted alkene is this one, because this is 1, 2, 3. This is tri-substituted alkene, tri. this is an alkene where it is a di-substituted alkene. So we have two products, one minor and one major. So remember what we have done. From first we have to ring flip to C to get an alpha and a beta hydrogen that can be eliminated, and also it is antiperiplanar, so you can't get it from this conformer but rather from the same molecule. By just ring flip you get this conformer. This conformer is the one which is reacting to give you two products. Let's test this one. You have this, so how many potential beta hydrogens you have? So here you have hydrogen and hydrogen on this carbon, one beta hydrogen which is antiperiplanar like this, but this beta carbon doesn't have an axial hydrogen, which is a hydrogen is equatorial, so that's not available for reaction. So this actually gives only one product. So if you just use a base, OCH2 CH3, the elimination product of that would give you this. See, this is the major product. It's only one product you have. This gives two, but the trans one gives you one. So based on where things are and how the conformations are possible to give you with the antiperiplanar arrangement, the product or the alkene that you'd get would be various types. So here we have major minor product. Here is just one product, which is major, because you don't have another one. So remember, whenever you have an open chain in the Newman projection, you can rotate and see to keep the stereochemistry for E2 reaction. And if you don't have an open system, and if you have just a cyclohexane system, you need to show the right conformer. This is the reacting conformer. Here the reacting conformer is this. So first you have to know how to ring flip things without a mistake or an error. Then you could just continue with the reaction. So there are 2 points you have to consider when you do an E2 reaction. The E2 reaction is a single step reaction. That's why you have only one antiperiplanar arrangement that could give a product. So we'll continue to the next step. So previously I have considered the antiperiplanar with open chain alkanes that can rotate. Now this is example of antiperiplanar arrangement in cyclohexane system, which are rings that cannot rotate, but just do ring conformation, meaning that chair conformation. This is a chair flip. Chair flip. This is chair flip. You do chair flipping to get a beta carbon or a beta hydrogen and an alpha halide, chloride or bromide, that is antiperiplanar. So the trick is to put the halide first in axial position. So you have to choose minimum that the chloride would be on axial position. Then you'd find any hydrogen that's also axial to be antiperiplanar. That's how you would solve problems in cyclohexanes with E2 reactions. Okay, before we conclude this chapter on elimination, I just want to do one more example with cyclohexane for E2 reaction mechanism. And finally, we conclude also by doing double elimination to form alkynes, not alkenes, but two double bonds that can be made. First, let's just solve like what we have just done previously in cyclohexane. Here we have this compound. It's a trisubstituted cyclohexane. Let's just do it in chair conformation first. And the question we are asked is to give the elimination product. This is potassium tertiary butoxide. It's a strong, bulky base. We are using a strong, bulky base. That means it is an E2 reaction. So now first let me just write this in the proper chair conformation. If I try to draw it in a chair conformation, that compound looks like chlorine is down. I will put it down like this. Metal in the next carbon is up, so this would be methyl group. And ethyl group is up also. So ethyl group would be up in the next carbon. This is ethyl group. So this is what the chair conformation looks like for this compound. As we have already discussed, for E2 reaction, the halide, which is the alpha carbon, the halide on the alpha carbon, should be anaxial. That's what I suggested. So to do that, let's ring flip without making any mistake to make the chloride into axial. The ring flip of this equivalent structure would be, if you just ring flip this is what it looks like. Chlorine is axial right there, and the next methyl group would be equatorial, was now being axial, right? Ethyl was axial. The next conformer should be equatorial, so it would be this. So this is a conformer. So you should be familiar by now how to ring flip without making any mistake on how to flip the conformer. Now we have set it up for a reaction. So how many beta hydrogens we have? We have one hydrogen here, which is actually equatorial on beta position. And here we have one hydrogen here and another hydrogen, but we'll choose which one would be reacting in the E2 reaction. So if you just look at here, antiperiplanar, there is no hydrogen. This is carbon. So that there is no any periplanar hydrogen to eliminate chloride from this carbon. So no reaction with this. So this one is not periplanar. If it had been axial, yes, but it is in the equatorial position, so they are not in the same plane. The chlorine and the hydrogen are not on the same plane, so that doesn't work. So there is no reaction from this carbon. But here you have this hydrogen, which is on the same plane and periplanar, anti-periplanar. This hydrogen and this chlorine are anti-periplanar, and they are on the same plane. This is on this board. If you just consider chloride to be on this board plane, this hydrogen is also on the same. So if you just use potassium tertiary butoxide, or TBU, that is a strong base, that would abstract that hydrogen. A double bond form here, and this chloride comes out. So the structure of this compound looks like, so the double bond is right here, CH3 is still there, and the ethyl group is here. let me check. Yes, so that is the double bond right here. CH3 is next on that carbon, and ethyl group. So this is the only product. This is only major product, only. You don't get the other conformer, for example, even though it's a more stable conformer, which is CH3. By eliminating this hydrogen, you would have gotten this product. But this is not observed because it's not antiperiplanar. No, not a product, not seen, not observed or not seen. This product is not seen. So X. But if you are asked which compound is more stable between these two, this would be a more stable one. But because the reaction cannot happen, this reaction cannot produce this product. This is made by other mechanism. No E2. No E2 product. Like this. This is only E2 product. Okay? So that's how the selectivity of the reaction, which is look for antiperiplanar arrangement on the reaction. So the question mark answers this is the E2 reaction product, but not this one, even though it is a more stable alkene, because this hydrogen is not antiperiplanar to that chlorine, so that cannot be eliminated to give this. So this is not the one to be seen in the product. So to conclude finally, remember there is also a double elimination. If you have two chlorides here, for example, that potentially two hydrogens, you could lose those by elimination. If you use a strong base, for example, sodium amide, potassium tertiary butoxide, and in DMSO, for example, polar aprotic solvent, you could effect basically a double elimination. So this is just to conclude. But I want you, at this point, I want to show you one terminology you need to remember. When the halides are on alpha and beta, meaning 1-2 position, they are called vicinal or neighbors. So these are vicinal halides. They are on 1 and 2, but when the chlorides are on the same carbon, they are called geminal halides. For anything, it's for substituents. If we say they are geminal, we mean that they are on the same carbon. But if we say those are vicinal, we mean that neighbors, 1-2 position, one next to the other. So if you have vicinal halides or geminal halides, you could generate double elimination that forms an alkyne. Not alkene, two double bonds, it's called alkyne, triple bond. Alkyne can be made by double elimination, 2 E2s. You can undergo 2 E2 eliminations, meaning that, for example, if you take this hydrogen and the base comes in, abstract this chloride leaves. The next alkene, you do one more. If you have the base, still this hydrogen would eliminate this one. So you have both this and this can be eliminated to form 2 double bonds. So that's an alkyne, not alkene. Here also in the vicinal halides, you could lose like this, and then you could lose like this. So both can give the same alkyne. Both vicinal and geminal halides could give you an alkyne, which is a triple bond, using a strong base and a polar aprotic solvent. So this would conclude our chapter on elimination reaction, both E1 and E2. E1 being not very useful as a synthetic method because E1, by forming carbocation, is prone to substitution reaction by SN1, but E2 is usually used for organic synthesis to make alkenes and alkynes. And also an E2 reaction is stereospecific, meaning that it requires antiperiplanar arrangement in the reaction. So with this we conclude elimination reactions. Thank you.